We are doing vectors. Alright, so we will have to come back to chapter 5 because we're skipping over to chapter 6. Vectors is going to be a shorter chapter, so vectors. Okay? Now, luckily for you, they start out fairly simple. So what is a vector? Well, a vector is a magnitude and a direction. So vectors are typically used to describe motion, linear motion specifically, in physics. So our magnitude is how much? So our magnitude could be something like velocity. It could be force. It could be work. You know, all those different things. Direction is, well, which way? Alright, so now in physics, I'm pretty sure that this is called 0 degrees, and this is 90 degrees, and this is 180 degrees. We do it like this. But for us, since we're in math class and we're just fixed in our ways, we'll just count our degrees like we're used to. 0 degrees, 90 degrees, 180 degrees, 270 degrees. It really doesn't change much of what you do, but it does change how you would line up your directions a little bit. So we'll just do our normal graphing. Alright, well, what would be a vector? Well, this could be a vector. So there's a vector. Notice that it is an arrow. The arrow is indicating that it is a vector. And this here, this would be our magnitude. And that really is just a distance. So you can use your distance formula to figure out the magnitude if you want. The magnitude you could also figure out with absolute value. So there are some things about vectors that we need to be aware of. First of all is vector transport, which sounds like something out of Star Trek. It basically is. Alright, so vector transport. What we can do with a vector is we can move it, we can move them. I can't spell. I can't even spell move. We can move them anywhere, and without changing their direction or their magnitude. And that's going to be very useful for, like, if we want to add two vectors together. So I'll just illustrate with a picture. Let's say I have that same vector that I drew right there. And notice where I moved it. I moved it to the origin. And maybe I have this other vector. Maybe I have this one. And I want to add those two vectors together. Well, I could take this vector and I could move it down here to the origin and add it that way. But it's by far easier to take that vector and put it over here. So what I end up with, do it in a different color. See, I keep its direction and its magnitude. I keep those the same. So I line it up tip to tail, and then my answer is just from the origin up to here. I meant to do that in red. That's my answer. If I add those two vectors, this is my answer right here. That's the vector sum of the green vector with the blue vector. That's we call that the resultant. Okay. Let's say I want to find a vector, because we're used to a coordinate plane. So maybe I want to find a vector. Boy, my writing is very terrible. We're going to find a vector that is drawn through 2 points. So that's what we're going to do. And to illustrate what's going on, I'm going to go ahead and write the 2 points over here. Get rid of these.
Turn your haircut over.
Okay, so let's say the first point is -4, 2. We'll call that point A. And the other point is -1, 6. -1, 6. 2, 4, 6. So here's point A, and here's point B, and it's drawn from A to B. So we're getting the vector from A to B. So we would use this notation. Do you see this? It's not quite a ray. You might remember from geometry doing a symbol like this, except you had that little extra thing there for an arrow. A vector is just going to be that half arrow. So we're drawing the vector from A to B. So A is where we start, and B is where we end. But if I want to find the vector and actually represent it, I'm not going to do, I'm not actually going to figure it out by starting at A. I'm going to start at B. So I'm going to do point B minus point A to figure out what the vector actually is. So here's my vector notation. Notice it's not parentheses. It's this, I don't know, less than symbol. So to get the x component, I'm going to do -1 minus -4. And then I'm going to do 6 minus 2. So if I want the vector from A to B, and I want to know how that's represented, I actually take B and subtract A from it. I take this end point and subtract the origin. So it's going to be the end minus the start will give us our vector. So our vector is the end minus the start. So in this case, I'm going to get 3, 4. That's the vector. And notice the notation. Okay, that tells me it's not a point. I can draw it. So 3, 4. 3, 4. See, notice I can transport that vector any way I want. By writing it in this notation, it basically orients it at the origin. But I can move it around wherever I want. So how do I do this? To find a vector drawn from 2 points, say from point A to point B, it is going to equal point B minus point A, comma, point B minus. So we have our x components and our y components. And it doesn't matter what the letters are, you just basically subtract point B, point A from point B. B minus A. And that's how we get it. So what if I had the point A is 2, 3, and the point B is 7, 5. And I draw a vector. So I want vector AB. I'm going to do 7 minus 2, comma 5 minus 3. And my resultant is 5, 2. All right, what's vector OP? Yep. -3 minus 3. and 6 minus 5, so it gives us the vector negative 6, 1.
PreCalc is overpowered.
Okay? Maybe I have something like this. Maybe I have vector AB, and I tell you that vector AB is 2, negative 4. And I tell you point A is 4, negative 3, and I want to know, well, where's point B? Well, we need to remember how we got this to begin with. It would be bx minus ax, comma, by minus ay. I know in the end I got 4, or 2, right? So that means 2 must equal b minus 4. And that must mean negative 4 equals, well, by minus negative 3, so plus 3. Do you see where I got that? I'm saying in the end, after I figured it out, I got 4, and at the end I got I got 2, sorry. I got 2, and at the end I got negative 4. So I said, well, I subtracted 4 from something, and I added 3 to something. So my starting vector, or my point, my terminal point was 6, negative 7. That's point B. So your book calls this the initial point, and this the terminal point, which means end. It's the same thing, initial, start. Okay, we could do it a little bit different. I'm going to have the same resultant vector, but now I'm going to say instead of A being 4, negative 3, do we get all this down because I'm about to erase it? Okay. So instead of having A be 4, 3, well, maybe B, my terminal point, is 4, negative 3. So point B is that. And I want to know, well, what's point A? What's the initial point? Well, I'm going to do it the same way. When I set this up, in order to get this vector, that means I took bx and I subtracted ax. It means I took by and subtracted ay. Well, this got me 2. But this time I know bx is 4. So I subtract ax from it. And right here, I know that I got negative 4. So it means I take by, negative 3, and subtracted ay from it. Subtract the 4. So ax is 2. And add the 3. And then that means ay is 1. So what's my answer? 2, 1 is point A. But notice, in both cases for this problem, the vector that I ended up with is the same. And that just reinforces the idea that you can move these vectors anywhere you want. So what do you need to know how to do so far? Given 2 points, get a vector. Okay? Given a vector and a point, give me the initial or terminal point. You with me so far? We good? Okay, let's find magnitude now. Alright, so before I go ahead and show you all that, I just want to show you really it's just an application of Pythagorean's theorem. So let's say I have the vector defined by the point. So I have a vector AB, and you don't need to write this part down. And let's say that it's point A. Let's say that was 4, negative 1. And let's say point B is let's say 6, 3. So 4, negative 1 is right here, and 6, 3 is right here. So this is the vector that I'm talking about. So what I can do is vector transport that and put it over here. You see what I did? So what's this length right here? What's this length right here? 2. And what's this length right here? 4. And you should see, oh, we have a right triangle here, which means I could get this by Pythagorean's theorem. A squared plus b squared equals c squared. So 4 plus 16 equals c squared. So I get 20 equals c squared. And then what do I do? So what's the square root of 20? Well, 2 root 5. So this is 2 root 5. So what's the magnitude? What's this length? Okay, its magnitude is 2 root 5 by Pythagorean's theorem. Now, here's how we could do this. First we get our vector. So to get our vector, I do b minus a, right? So 2 and 3 minus negative 1 is 4. So there's my vector. That's what the vector is. The magnitude, which is going to be represented like this. The magnitude of vector AB is going to be the square root of the x component squared plus the y component squared, which you can see is right here, and then we ended up square rooting it, which is square root of 20, which is 2 root 5. Okay, so how do we do this? Magnitude of a vector is going to be the square root of its x component squared plus its y component squared. Or if you want to know where we get those, we do x2 minus x1 squared plus y2 minus y1 squared. And it doesn't matter the order of those. Just be consistent. Now magnitude you can think of as a length. Length or strength. So here's a situation that we might have, and we're going to work towards figuring this out. Here we have a cow, and being the great Southerners we are, we're wrangling up this cow, and so we have Josh pulling at the cow this way, and then we have maybe Jarrett's pulling at the cow this way. They're trying to get this guy under control, and maybe Cameron's pulling at him this way. And what we would ask, the question we would ask, well, which way does the cow move? Okay. So that's a physics problem, and we would use, these are all vectors, and each person has a different strength and they're pulling in a different direction. We can figure out which way does the cow go. Now, yes, I know you're not sitting there wrangling a cow trying to figure out which way it's going to go as you're pulling at it, but a physics problem is going to have, like, maybe a more realistic situation would be is if you're trying to move a large object, say, on the ocean. And you want to know, well, how are we going to pull this thing? You wouldn't want to just tie it up and then pull and just chance it, because you're going to have waves and things like that. So you want to know how much force and how fast to go and which way to go to pull something before you get started. You want to have an idea of what to do. So that's what we're going to be working towards. All right. So to get there, we need to be able to do vector addition and subtraction.
The cow will go to Josh because he's the strongest.
He dragged me again though in the cab.
Yep.
So vector addition really isn't that bad. If I want to add vector u to vector v, and I'm not giving you any, whatever. It could be vector a, vector b, it doesn't matter. I really just add their pieces. So if I had 4, 1 is vector u. And let's say vector v let's say that's -3, -5. It's really not that bad to go ahead and add these. 4 plus -3 is 1, and 1 plus -5 is -4. But maybe we need to show it graphically that that's the answer. All right, so my first vector was 4, 1. I've got to erase all this. My first vector is 4, 1. That's right here. Doesn't matter where I draw this. I can't emphasize that enough. I'm just choosing to draw it from the origin because that's easier. The second vector was what? -3, -5? Is that right? Which would be right here. So what we can do is take this vector, it's not letting me. Let me move you. Well, it's not letting me, for some reason. But I can take that vector and move it. And I'm going to move it over to here, and I line these up tip to tail. Tip to tail. So I'm going to take this and just move it, see, to the end right here. So I'm just going to pretend that this is my origin. So -3, -5. 1, 2, 3, 4, 5. See, I just moved this over. I just took it, and I'm like, nope, I want it over here. So then what's my answer? Start at the beginning and draw over. This is the resultant. Do you get the idea of vector transport? I take the vector and I move it, and I line them up tip to tail.
So how do you... Never. Like, I know like what you're saying.
So let's say I had 1, 2, and I wanted to add to that 3, 1. The answer is going to be 4, 3. That is the answer. I just add the x's and y's. But what I'm saying is, suppose you were told to show it graphically. You know, how do we get this using a coordinate plane? So what I'm telling you is, you're going to draw your first vector from the origin. Here's my first vector. 1, 2 is right here. All right, now when I draw this vector, yes, that vector would be 3, 1 right here. Okay, it would be there. What I'm going to do though is I'm going to count it from here and pretend this is my origin right here. 3, 1. Okay, right 3, 1, x, y. Okay, then what's my resultant? I start at the origin where I started from and connect to there. That's my resultant.
I gotcha.
Okay, so what about subtraction then? Vector subtraction. Well, it really is as easy as subtract the vectors. So suppose I wanted to do 4, 1. I'm going to use the same vector minus -3, -5. Well, then I'm going to get 7, 6. But what if I wanted to show it graphically? Here is what I would suggest you do. This isn't what they would even show you in another course, but it is by far the easiest way to do it. Graphically, switch it to addition. Okay? So instead of subtracting those, what I'd write is 4, 1, plus, I distribute that negative 3, 3, 5. And then I do it the same way as we did at addition. Do I need to show that again?
Yes.
Graphically?
Yep.
Okay, so do you understand what I mean about distributing that negative and switching to addition?
Mm-hmm.
Okay, this might go off, but I have 4, 1, right? So I'm taking vector 4, 1 and adding to it which vector? Is it 3, 5?
Yeah.
Okay, so I draw my first vector, 4, 1, right here. Boom. Now, pretend 4, 1's the origin. You with me? We're playing pretend. Count 3, and then 5. 1, 2, 3, 4, 5. Right there. Draw that vector. See what I did? All I did was I pretended that this point. All I did is I pretended that this was the origin. It's not, but I pretended. And then I counted right 3 up 5, x, y. Now my resultant is from the real origin all the way up here. That's my actual vector. Now you might be wondering, well, why do I even want that? Well, if I want to know the direction it goes. If I want to see the direction that's going to go. So let's say that this was the cow. Okay? And Cameron was pulling at the cow with this vector, 4, 1, and Jarrett was pulling at the cow with this vector, 3, 5. Well, where does the cow go? Here. Okay, that's the result. That's where the cow's going. Of course, the cow might resist you, so we might throw that into the mix there. You can add any number of vectors. It doesn't matter. So, and we can show all of them. So let's say we add a bunch of vectors. 1, 2, plus, let's go negative 3, negative 3, and let's add a third vector, maybe 4, 1 again. Let's add all 3 of those. I still do it the same way. I can just add all these. So let's add all of them. So 1 plus negative 3 plus 4. Well, what's that? 2. And negative 2 minus 3 plus 1. Well, that's going to be 0. So that's my result. But if I want to show it graphically, 1, 2 is this vector. See, I'm going to show this result graphically. Now, where is this vector, negative 3, negative 3? Down here, right? Now, what can I do with that? Pick it up and move it. You see what I mean? Now, where's this vector, 4, 1? 4, 1 is this vector. But what do? I pick it up and move it. Hopefully better, okay? And then what's my answer? From here to here. That's my answer. Now, I did that by picking them up and moving it. So 1, 2. From here, down, or left 3, right, down 3. From here, right 4, up 1. What's my result? This. And what do I predict by my simple addition? 2, 0. There it is, 2, 0. All you do when you're doing it graphically, tip to tail, or tail to tip, whichever. That's all you're doing. And switch to addition. If you have subtraction, switch to addition by distributing. All right, next, unit vectors. A unit vector, this is probably the hardest thing that we'll do today, but it really,
We need graphic for this.
no. But it really is not that bad. Unit vectors are vectors whose length or magnitude, as implied by the name, is 1. These are very, very useful. We basically call these direction vectors. Of everything that we've talked about today, direction vectors are by far the most useful, because since they have a length of 1 all the time, the information that we essentially get from them is the direction only. Which means we can use that to scale how fast we want to go or how much force we want to apply in a certain direction. Alright, so getting a unit vector is, well, let's say vector u. Let's say I have vector u and I want the unit vector. Okay, that's going to be the x component divided by the magnitude of vector u, comma, the y component divided by the magnitude. Which looks really complicated. And you see all these u's here. Do you understand what I'm doing with this subscript? I'm saying vector, the x component of the u vector, the y component of the u vector. Do you see what I'm doing there? Okay. And this is the magnitude. So let's say I have vector, this vector, 5, 3. And I want the unit vector. So that's going to change the magnitude. Magnitude is going to become a 1. I want it to be a 1. What am I preserving? What I'm doing here is I change the magnitude to 1, but keep the direction. That's what I'm doing here. Alright, so first we need to find the magnitude. Well, what is the magnitude of this? Well, it's going to be the magnitude of 5, 3 is going to be the square root of 25 plus 9. Do you see where I got that? Pythagorean's theorem. So square root of 34. That's the magnitude of this. So what's the unit vector? Well, the unit vector of this is going to be, I don't know why it doesn't actually take my answer. The answer is going to be 5 divided by root 34, comma, 3 divided by root 34. Now, I know that we would normally rationalize. For this chapter, you are not going to rationalize. The reason being is that we're testing and looking for that you understand that you are dividing by the magnitude here. And if you rationalize, it just gets unnecessarily sloppy. So you're not going to. Any questions on how I got that? Alright, let's try another one. Let's say I want the unit vector for negative 8, 4. This does not have a magnitude of 1. But I want to keep the direction but have a magnitude of 1. So I find its magnitude first. The magnitude, I square that, 64 plus 16. Get root 80. Now prime factorize that. Let's see here. Just leave this. 8, 10. 8 is 3 2's.
There's
2 and 5. So it's 2 to the 4th times 5. So I get 2 squared. You remember doing that? 4 root 5. Alright, so that is my magnitude. So that's the magnitude of this. but I want it as a unit vector. So I take both the components and divide them by 4 root 5. Now, just because I said you don't have to rationalize doesn't mean you don't simplify. I go ahead and simplify that. 8 divided 4 is 2. And 4 divided 4 is 1. Okay? That looks good to me. Any questions? All right, we are done with part 1 of section 1.